All right, and the second thing we need to talk about today then is writing what are called net ionic equations. These equations include only those compounds and ions that undergo a chemical change in a reaction in an aqueous solution. But one of the more important reasons that we do this is to really focus on just those things that are undergoing chemical change. Okay, and before we write these net ionic equations, one really important vocabulary word here is spectator ions. These are things that do not take part in the chemical reaction and are found in solution both before and after. They're just watching the chemistry happen. They aren't actually taking part in the chemistry themselves. Now, how do we write a net ionic equation, you ask? Well, really good question. The first thing you're going to do is write the molecular equation. This is the type of equation that you are used to writing out. So your molecular equation might be something like what you see on the screen in front of you here. We've got zinc nitrate reacting with ammonium sulfide to form zinc sulfide and ammonium nitrate. There shouldn't be anything that's too unfamiliar with that. Everything is written together using the nomenclature that we're used to. That is step one. Our second step, though, is once we have the molecular equation, is to write what's called a total or complete ionic equation. And when you do this, you just take all of your soluble ionic compounds and write them as dissociated ions in solution. So as you take a look at your screen, notice that I've got several of the reactants and products that are aqueous. Notice then we will write our complete ionic equation in which we separate out all of those things that are aqueous into their individual ions. Always! Notice that when I did this, I recognize that in my zinc nitrate, there is one zinc ion and two nitrate ions. So when I put that into solution, for every one zinc ion I get, I'm going to get two nitrate ions. Similarly, with ammonium sulfide, I'm going to get two ammonium ions for every one sulfide ion. Check how I've kept the zinc sulfide together because it is a solid, and so I don't separate them into their ions. And then finally, with the ammonium nitrate, I put two ammonium ions and two nitrate ions, even though the ratio in the equation is 1:1. Do this because in the balanced chemical equation, the coefficient in front of that compound is 2. And so as you look at your equation for both the molecular and net ionic, you should see that we're still following the law of conservation of mass. Once you have written out all of your aqueous compounds as individual ions, your third step is just to go through and cancel all the spectator ions, which again are those ions that are just watching things happen. They're the ones that are going to be aqueous on both sides of the equation. Now, as you take a look at zinc, the zinc ion does not appear as an aqueous ion on both the reactant and product sides. It goes from aqueous to solid. So zinc is a playa. It is in the game, it is doing some chemistry. Notice, however, that nitrate appears as an ion in both the reactant and product sides. It is a spectator. It's just watching it happen, just watching the chemistry happen. An aqueous ion before and an aqueous ion after. Same thing with the ammonium ion, aqueous ion before, aqueous ion after. Spectator ion. Our sulfide ion is another player. It's actually doing some chemistry. Our final step then is to rewrite the final equation without those spectator ions. That will give us what is called the net ionic equation. Just the things that are involved in the chemistry. So my net ionic equation is what you see here. We've got the aqueous ions in the reactant side that form the solid precipitate in the product side. That is my net ionic equation.